Hi all, my name is Aathira Menon. I'm a research scholar at National Institute of Technology, Karnataka, and my area of interest is deep learning applications for wireless sensor network. Today, I'm going to take up a hands-on session on getting started with machine learning using Python. So the contents for the day are, we'll be dealing with what is machine learning, why we need it, and we'll be checking some real life examples and going into the terminologies that are essential for somebody who is getting into a machine learning domain. Then we'll take up some algorithms, and based on these algorithms, we'll have the illustration on Python codes. So let us understand what is machine learning. So it is not something that has evolved in the past 5 or 6 years. If you can see the statistics, it shows that machine learning has been there in the science since 1950, since Alan, who has developed a Turing test, which means that he wanted to test how intellectual a machine is in making decisions that are indistinguishable from that of humans. So AI and the artificial intelligence is actually deals with building machines that are capable of performing tasks that typically require human intelligence. So machine learning actually comes under artificial intelligence, which deals with these algorithms that lead into the automation of any application. Okay, so if you can see that since 1950, there has been a tremendous evolution in machine learning, starting with neural network and then to the ELIZA developed by MIT, then going into the Q-learning, which comes in a reinforced learning, and then into the development of artificial neural network, and then to the K-nearest neighbor, then to the LSTM, and to the Google Brain and the Facebook's deep face. The machine learning or the artificial intelligence is still revolutionizing. So as I said, artificial intelligence forms the higher umbrella under which the machine learning forms, and deep learning, which comes as a subset of machine learning. So let us see what is artificial intelligence. So it's a program that can sense, reason, act, and adapt. So what is machine learning then? These are the algorithms whose performance improve over time with more amount of data. So what is deep learning then? So deep learning is actually a subset of machine learning that develops the predictions or the learning capacity by mimicking that of the human intelligence. So if you can see machine learning, it's actually connected to numerous applications. Say, you have some machine learning algorithms which does the learning, you improvise the learning, you analyze the data, you make autonomous systems, and then you have neural networks, you do the classification process, you have data mining, you have artificial intelligence. So when I say machine learning, there are plenty of things that fall under this umbrella. So why we need machine learning? Because we have already seen we have a high computational, the processes or the statistical model. And amid it, why do we need a machine learning? So if you see a traditional programming, it's actually going to, perform, say you have a CSV file and you have certain data points, say X, and then you have a target point Y, and you are going to write something like, if you want to do a summation of these two cells, what you're going to do, you're going to write a program wherein it does X of X1 plus X2, and then you're going to copy the same algorithm into the complete data set. So that means you have a data, you have a program, and then you feed it in the computer, which gives you the output. So output is nothing but it will fill these data points with the summation of the consecutive cells. But what does machine learning do? So in terms of machine learning, we are actually going to pass the X data, the Y data, the summation data points as well. And we expect the machine to come up with this equation, which is going to be a generalized, the result for any data of this sort. So that is the difference between a traditional program and a machine learning program. So I hope that is clear. So now going into a real life example. So if I say machine learning, artificial intelligence, these things sound very fancy, or they look like it has never been heard, or we have never been influenced by these machine learnings or artificial intelligence. So I would break down this humongous word of machine learning into a very simple example. So that is the one of the application of machine learning that has hit heights is nothing but the recommendation system. So if you see, suppose you have your Amazon or a Netflix application and you watch a particular movie today, and then it's going to give you some the similar movies or the similar products as a recommendation to you. So how does this work? So this actually works on machine learning. So you see, you have a user A and you have a user B. So they have got similar traits. That is, the movies that are watched by A and B are of same genre. So what the machine recommendation system does is, the movies that are watched by user A will be recommended to user B because they share a similar interest. Now there is another another type of filtering, that is similar movies. Say the user A has watched comedy genre or a movie of comedy genre. There are another movie which fall into the same genre, and that gets recommended to the user because we know that he has watched this movie, so he might be interested in this movie as well. So that is how the recommendation system works. So anybody who gets into the machine learning domain has to have these words on its hand tips. So I would say, these are actually the building blocks of any machine learning model. So starting with model, a feature, target, a training, prediction. So I would start with feature. So features are nothing but the input. So if I say I have, I have taken an example of a CSV file. So similar to that, I'll quote the example. So say I have a CSV file over here, which has got X and Y. So this is my X and this is going to be my Y. So my X is going to be the feature set. So these are the features of this particular use case, and Y is going to be my target or the outcome. And the input and outcome is actually mixed into a training phase. Okay, so I can, pictorially put it in this way. Say I have a model. Let us take it as a black box for now. So I'll have my X, I'll have my Y, which is getting passed to a machine learning model, and that is going to give me some predictions. Okay, so these are my predictions. So this is where my training actually takes place, and this is going to give me my predictions. So everything in a nutshell forms a model. So input, the target, the training phase, the predictions, everything put together forms a model. So model is nothing but a hypothesis. We are actually, it's an hypothesis because these are the analysis made by the model with respect to the data that we have passed. Okay. So next, going into the algorithms part. So as I said, machine learning deals with a lot of things. So in respect of its algorithms also, machine learning has four types of algorithms, mainly dealing with supervised, unsupervised, semi-supervised, reinforced. Supervised learning deals with two main algorithms, that is classification, regression, and unsupervised has clustering, dimensional reduction, density estimation. Okay. So we'll see in each of these in depth. Okay, so what is supervised? So when I say supervised, I'm going to supervise my model when it is training. So I have my model here. So it is going to take up some data here. Okay, this is going to take up some data, and I have a supervision over here. So this, let's say this is a supervision. So what is supervision now? So supervision is nothing but the labelings of the data set. So I'm passing the labels along with the data for my model to train. So that is the supervision that I'm meaning over here. If I see, as we saw in the previous slide, supervised learning has two types, that is classification and regression. So classification means if these data points are passed into the machine learning model, and if I label them as dots and cross marks, it is going to train and segregate itself into two blocks, wherein the dots are segregated as block A and the crosses are segregated into block B. So it is classification. So say I want to do a regression. That means it's a continuous prediction, say from 0 to infinity. So these are my data points, and I would like to make a prediction. Prediction is nothing but finding the best fit line which gives the least the error with respect to all the data points. So this is the best fit that I can make with respect to satisfying all these data points. That is a regression analysis. So to make it further clear, I have an example over here. So you can see you have a label data. So what do you mean by labeled? So by label data, I mean to say, I am telling the computer that this is going to be tomatoes, this is going to be carrot, and this is going to be the bell pepper. So these are the labels that I'm going to pass with the data. So I would say this is my feature, and this is my labels. I'm going to give both of them to the model to train, which is going to make the prediction. So for predictions also, I'm going to give the test data. So the labels are already provided, and now the machine is going to predict whether it is a carrot or a bell pepper or tomato. Okay, so what is my supervision here? I'm supervising this in terms of the labels, like what is what. That is why it's called supervised learning. Okay, now let's see what is unsupervised. So as I said, supervised means I am passing the labels for the machine learning to understand what is what. So what does unsupervised mean? That means there is no labels passed for the model. So model itself learns from the data character. So if I say I have some set of data here, and for an unsupervised model, I would require my machine to cluster it into two chunks. That is, I don't want to I don't want the machine to tell what is these two clusters, but I want the machine to say these clusters are different from these clusters. So that is the clustering process that the machine does depending upon the data attributes. So it is not having any prior knowledge about what these clusters contain or what these clusters contain. Okay, again, I have an example for this. So a similar one. In the last example, we had passed a set of vegetables with its name. So now if you see, the vegetables are passed similar way, but the labels are not passed. So the model is trying to interpret and build algorithms depending upon the color, the shape, the size, the texture of these particular vegetables. So it's going to process for me and give me the output. So if you can see, I have my bell peppers in one cluster, I have my brinjals in one cluster, and I have my turnips in one cluster. But the model has not differentiated green bell peppers from red bell peppers because I have not given any strict labeling. So it has just clustered it, saying that this is one cluster which do not resemble this and which also do not resemble the turnip. So that is the idea of clustering, that is differentiating one group of elements from that of others. Okay, next you have semi-supervised. So we have seen supervised, we have seen unsupervised. So when I say semi-supervised, that means there is supervision, but not fully, but partially. So let us see what is it. So I have an input data here. You can see there are apples, bananas, and oranges. So the partial labelings are that orange and bananas are labeled, but I have not given the machine what is apples. So I've not labeled them. So both these data and the partial labels are passed, and my machine learning is going to learn. So once I say my apple is a test data point, it is going to predict it is an apple because it knows it is not an orange, it is not a banana. So it has to be the third class. So third class is nothing but the apple. That is the semi-supervised learning. Okay, next coming to the reinforced learning. Though the terminologies look very big or very fancy, but it's actually something that we have been, built on. So I would, I will prove this statement through an example. So, in reinforced learning, there are two main attributes, that is an agent and an environment. So agent is that particular, constitute of the model who needs to be trained, and environment is a set of criteria or the constraint that the agent has to learn on. So the actions that agent give according to the environment will be rewarded or penalized, on which the agent gets, rectifies its mistake and improvises. So with this reinforced learning, let me take into an example. Say you have your pet dog and you want to train it. So you want to train it in such a way that if you throw a twig, it has to go and fetch the twig and bring it back to you. So you have this as an agent. The environment, nothing but the throwing of the twig, and your actions are the environment for the dog. So once you throw the twig, the dog is going to fetch the twig and give it to you. So that is the correct action expected by the dog. So if it is giving the correct action, it will be rewarded by its favorite snack. In case if it fails to fetch the twig, then it is going to be penalized. Say, you are going to cut the snacks for the next 2 days. So this is a penalty that the dog is going to get, so that next time when you throw the twig, it is going to remember that it has to capture the twig and bring it back to you to avoid the penalty. So that is how reinforced learning works, which is quite similar to how we have learned, from our childhood. Okay, so coming to the Python toolkit, we have numerous, development environments for Python-based applications. So we have Anaconda, which provides Jupyter, the Spider IDs, and then we have Google's Collaboratory, which provides you the power of GPUs to train your heavy models. Then you have Kaggle, you have Visual Studio Code. So you have plenty of such development environments. You can choose the ones which are of your comfort. So for today's session, I'll be working on Spider. Okay, so which is a derivative of the Anaconda navigator. Okay, so before we get into the illustration code, I would like to throw a light on the steps that are followed to develop any machine learning model. So these steps remain same for any machine learning model that you take. So initially, we need to gather the data for the particular use case, and then we need to prepare the data. We need to choose a training model. We need to train it. We need to evaluate the model. We need to tune the hyperparameter and do the prediction. So for any model or algorithm that you will be taking up in the future, these steps remain the same. Okay, so in 7 simple steps, you can build your own machine learning model. Okay, now let us get into the Python code. So for today, I have basically brought into 3 algorithms, which are from supervised learning under classification and regression, and then one under unsupervised learning. So I will take you into the idea of the each of these algorithms first, and then we'll go into the script or the code. Okay, so first algorithm that comes under supervised learning is a decision tree. So when I say supervised learning, that means I'm passing the labels for my training data for the model. Okay, so that is what I mean by supervised, as we have already seen it. So the algorithm is termed as decision tree. So if you can see an example over here, this looks like a tree. That is, if you consider this as a root, and if you take these as the branches and these particular decision nodes as leaves, then it will resemble a decision tree. So now to split this decision tree, or to find the root node, we have 2 particular methods, that is a Gini index or the entropy. So Gini index is going to give us the measure of the purity of that particular node. So say this is a node which has got the highest amount of purity or the highest probability. That means the Gini index of this particular node is high, which means my node is very pure, which is an ideal case for it to be the root node. Suppose if I'm using the entropy, which deals with the randomness associated with the node. So I mean to say, if I have to make this node as my root node, I expect it to have the least randomness. So actually these two are actually the negation of each other. So say I'm using one of them as the dividing criteria. So if I say, am I hungry? My answer is yes. And there is another node. Can I spare 250 rupees? Yes. Then you can order food from Swiggy or Zomato. Okay. If not, then I have to cook and eat. Okay. And if I'm not hungry, what do I do? Go and sleep. So this is a typical, decision tree. So now let us get into an example of it to see what a decision tree actually looks like and how we can model it. Okay, so this is my decision tree code. So actually, I've made it very simple so that any beginner coming into the course can actually get a grip on the the machine learning models. Okay, so this is how the console is going to look like. So I'll be clearing the console first, and I'll remove all the variables out of here just to make it afresh. Okay. So I'm going to clear the console. Okay. So as you can see, this is my scripting window, and this is my variable explorer window, and this is my console. Okay, so you can actually do line-wise code running just to see if you're a beginner. I would recommend you to go line-wise so that you understand what happens in each line of the code. So for this, you can actually use your control plus enter to do it as a run-wise. Or if you want to run it as a whole, you can use this green play button, which runs the whole script and gives you the outcomes as and there where you have written. So this is actually a decision tree classification problem that I've dealt with. So I'm going to import my necessary libraries. So I have Pandas, okay. And then I have the decision tree classifier from the Scikit-Learn module. And then I'm having a train test split Then I'm having a metrics library, and then few of the other metrics that are essential to assess the performance. So let me run these imports first. Okay, so if there are no errors, you will have the, the console comes into the next jump or the next run count. So if there are error, it's going to show you some error which you need to fix it and continue. Okay, so I have certain columns defined. So I'm having a diabetics.cve dataset which has got headers like pregnant, glucose level, the blood pressure level, the skin temperature, the insulin level, the body mass index, the it is actually the temperature pedigree, and then the age, and then the label. Okay, so the label is actually which corresponds to whether the person is diabetic or not diabetic. So we are actually dealing with the Pima diabetic, which is actually a kind of diabetics that are most commonly in the Pima Indians. Okay, so I'm going to run these column names. So again, I'm doing line wise run. So you can see in the variable explorer, these column names are done. I mean, the same. So if you double click on it, you can actually see what are these columns, how many columns are there, what type of columns are these, what is the size of each of these column names. Okay. So, and then I'm going to use the Pandas library to read a CSV file whose path is given as follows. Okay. So I'm going to read the CSV file. I'm going to use pima.head, which actually gives the first 5 readings of my dataset. Okay. So this is how my dataset is going to look like. Okay. Now what I'm going to do is, as you can see, there are 2 headers displayed, and I do not want the headers to be, repeated. So I'm going to remove the first row from this data frame. Okay, now if I print it, I am having the original column names which I had specified. Okay, now I'm coming to the feature columns again. So this is nothing but, if you can compare with these feature columns to the column names, you can observe that the label element is removed out. So the reason why the label element is removed out is because label is actually my outcome. So that becomes my target variable. Okay. So the reason why I have removed it from the feature columns is because once I run this feature column, okay, I want all the data points adhering to pregnant, insulin, BMI, age, glucose, BP, and pedigree to fall under a variable termed X. Okay, and the label which is left out to fall under Y. Okay, so this is my X and this is my Y. So if we can see, Pima has got 768 rows and 9 columns. Okay, and X is going to have 768 rows and 7 columns, and the 8th column is corresponding to the target. Okay, so I hope that is clear. So now, as I already told, we have to train the model and then we have to test the model. So we need to keep some data for testing and some data for training. So I am actually splitting my whole X and Y into 70:30 ratio. That means my test size is 30% and random state is going to be 1. So what is the importance of random state? So random state is a variable that helps you keep the uniqueness of a model. Say the same code I'm giving it to you, and if you are suppose running it without this random state, you'll have slight difference in the values because the training is taking in a different way and a slight different way. So to get the same results, to get the strictly same results, we are giving the random state a particular number. Say if I run it again with a value 42 or 260, it's going to give me a little bit different value than what it gives for random state equal to 1. So this is a test and train split function that I've taken from Scikit-Learn, which I've imported over here. So let me run this and I'll be getting 4 variables, that is X train, X test, Y train, and Y test. Okay. Now I'm going to make a decision tree based on Gini. So Gini index is the default dividing parameter that the decision tree uses. That is why I'm not specifying it inside the decision tree classifier. Okay. So by default, it's going to take Gini, and then I'm going to call, this is a classification object that I've created from decision tree classifier, and I'm going to invoke dot fit function on X train and Y train. Okay. So this is the training that has happened, and now it's the time for testing. So I'm passing the X test and I'm going to predict what is the Y predict. Okay, this is the predictions made by the model. So now let us see. I want to make an accuracy test between my actual target and my predicted target, which is going to say how close my model is able to predict the results. Okay, so let me print the accuracy. So the accuracy is around 66% in predicting the diabetic classes. Now let me see the classification report. So the classification report is one of the the important parameters when you deal with the classification. So it gives you a straight a depth analysis. So you say you have two classes, say 0 and 1, and for class 0 the precisions and recall values, the F1 scores, and the number of elements that support this class are shown as here. Next, you have class 1. The similar analysis is done for class 1 as well. Then you have accuracies. This is an overall accuracy, and this is the macro average accuracy uh, class-wise, and this is the weighted accuracy class-wise. So these are the number of support vectors, support data points that attribute to these accuracies. So if we can add these two things, it counts up to 231. So I hope that is clear. Now, we have done it with Gini index. Let us see how the model behaves if I change into entropy. So here, if you can see, here I am passing the criteria to entropy, and I'm giving the number of depths of division to 3. Okay, so let me run this now. The similar process. Okay, I'm going to train my model on the same data set. I'm going to predict the model in the same data set. And now let me print the accuracy of this model. So you can see the accuracy of this model has become 77 when compared to 66, which was gained by Gini index. So there is definitely an improvement of accuracy when you have used an entropy here. Okay, so now let us see the class-wise analysis using a classification report. So if you can go back and compare, here it is 72, 77, and 74, whereas here it is 80, 85, and 82, whereas the support elements are kept constant. So on an average, there is an improvement by changing the division parameters. This is how you can build a very basic decision tree classifier. Okay, so there are many attributes that come under decision tree classifier, which you can definitely go back and explore. So taking to you in a gist, I can say there are criteria. There is a splitter which says the best split, the maximum number of depth, the minimum sample split, the minimum sample leaf, the weight fraction leaf, the impurity decrease, the class weight, and many other parameters that you can tweak to make your model reach a better accuracy than 77%. Okay, so this is with decision tree. Now let us go back and see what is the next algorithm in the plate. Okay, so we have a supervised learning again, and which is nothing but a linear regression here. Okay, so linear regression is nothing but a simple, a line curve, which I've already shown you. That is y is equal to mx plus c. Okay, so what is my m? M is nothing but my slope. Okay, and x is my data point, okay, or the input variable, and c is going to be my intercept. Okay, so the c is my intercept, and m is my slope. Okay, so let me see how a curve with y is equal to mx plus c looks like. Okay, okay, so yeah, so let me draw an axis here. Okay, so this is a curve which says y is equal to mx, okay, plus c. So if I say what is an intercept here? So intercept is nothing but c, and the slope of this particular line is my m, and x is nothing but the data point, okay, on which the lines have been formed. Okay, so this is nothing but a simple straight line curve, which we all have been learning since our 8th grade or 9th grade. Okay, so this is a similar the linear regression is actually a similar analysis when you compare it to this kind of line curve. So as I said, we have y is equal to mx plus c over here. Okay, now let us try to correlate between this equation and this equation given. So y is again a dependent variable. Okay, so that is right. We have x, which is an independent variable which varies, and depending upon this x and this equation, the y is going to be valued. So that is a dependent variable here. And then we have an intercept here, which is again this c term. Okay, and then we have a slope coefficient, which is again a slope function, and the independent variables. This part is actually done. Okay, we are very familiar with this part. So what is this epsilon I? So epsilon I is nothing but an error function. So I would like to put it in this way. That is, I have an x, I have a slope, I have an intercept, using which I can find out what is my y. Okay. So let me see, I am using this as y hat because y hat is approximately equal to y. Okay. So this approximation can be removed if I remove this epsilon from here. Okay. So that is the error. So if I remove this error, that means x has enough knowledge to predict y perfectly. So that which becomes what? Y cap is going to become equal to y. So that means there is no error term. So that is why that is actually an hypothetical state. You cannot predict something perfectly without any error. So just to add this error term, we are using this epsilon naught. Okay. So not epsilon naught, it's an epsilon I, the random error component. Okay. I hope that is clear. So now let us get into the script. Okay, again, we have a similar one. So I have a script dedicated to linear regression. Okay, let me clear the console first. Okay, and I'll be removing all the variables also. Okay. Okay, so we are ready for the training now. So as similar to the decision tree, now I'm going to import the required libraries. Okay, so I'm again doing a line-wise execution here. So now I'm going to predict the salary of particular a firm or an organization given its data set. Okay, now I have a .csv file which I'm going to read and feed it into a data frame. Okay, so you can see this is a very simple example wherein there are years of experience against salary. So depending upon the year of experience, the salary has been modeled. Okay, so this is, if you can see from the previous curve, the previous example, you had whether it is a diabetic or not diabetic, but here the values or the target element is continuous. That means you need to have your model to predict these values continuously rather than a class. Okay, that is a difference between regression and the classification. Okay, so now I'm going to use an ilog function, okay, to give these years of experience into X and salary into Y. So this is actually a term called slicing, which slices your data frame into the required number of rows and columns. So now I'm trying to say all rows and columns except the last column. So that means to say there are two columns and I don't want the salary column to be included over here. So I'm just taking the number of years into X and the salary amount into Y. Okay. So now I'm running that as well. So one feature that I would like to introduce in this script is that, as I already told that, your analysis of Y is equal to MX plus C is actually a linear one, right? So if I say linear one means what? If my value of X is say 100, this will have an impact on the value of y that is predicted. Okay. Say if my value of x is 0.001, this will again have a numerical effect on the value of y predicted. So that to rule out this difference in the magnitude of the data point, what we are going to do is we are going to normalize the data points before we give it into the training model. Okay, so to do that, what we're going to do is we are going to invoke a library called standard scalar, okay, which is going to scale your data point or normalize your data point with respect to the the minimum and the maximum value present in your data. So I'm using this fit transform object, the library from standard scalar. I'm going to create an object of a standard scalar on which I'm going to invoke this fit transform, and I'm going to transform X and save it back into the same variable X to overcome any extra memory uses, because I am not interested. Okay, I'm sorry. So I see, if you can see there is an error. So you need to fix it. So the error was I have not invoked this standard scalar. So I need to invoke this and then I need to run this again. So now it is perfectly fine. So I can show you the difference. Okay, let me just put this again. So I'm just giving it the original data and I'll just show you what X looks. Okay, X is nothing but a number of years. Okay, it looks like 1, 2, 3, 4, 5, 6 and so on. Now let me show you what X looks once it has been scaled. Okay. So the value of x has now been scaled. That means it still retains its property, whatever the property it can. That means a difference in value of these two will give me the same as that of the original x, but I'm going to normalize it. Okay, there is a difference once I normalize it. And now I'm going to use the same training split library to bifurcate it into train and testing modules, and now I have a linear regression. So similar to decision tree, linear regression is again an algorithm that is again built on the Scikit-Learn. You have actually imported it as a regressor object. Okay, and now I'm going to train it. Okay, so this is a regressor is actually trained. Now let me predict it. Okay, so let me see what is my predictions now. Okay, so my predictions are so and so, and let me see what are my appropriate test cases. Sorry, the test value. So for 37,730, my predicted value is 40,870, which is actually pretty close. Okay, if you see the next data point is 1,23,188, and I predicted it to be 1,22,390, which is again pretty close. So our model is doing a very good job, okay, as of now. So let us see what is actually the performance analysis. So as I showed you, the regression actually deals with getting the best fit curve across your data point. So I'm using a scatter plot and scattering my x train and y train value, and again I'm scattering my x train and the predicted value from x train, and I'm going to plot the regression curve for training data. Okay, so let me see what we are going to get for training. So you can see that you have a training, you have a figure, you have this data point scattered, and this blue line is the best fit curve that you have predicted by your model. Okay, now let us see how good our testing plot is. Okay, similar way I'm using, in place of x train, I'm using x test and y test, and again here I'm using my x train over here. Okay, so let me just run over here and see. You can see I'm actually having the best fit line for the data points that are given. Okay, so you can actually tune these parameters. Again, as I said, I'm using a very basic linear regression model which does not have any other parameters other than its default mode. Okay, so you can actually play with other hyperparameters tuning and make this model a better one. Okay, so I hope the linear regression is very clear to you. Now let us see the last clustering model that we have. Okay, so the clustering model, that's a k-means clustering model. So k-means clustering model, let us break this word into three parts. Okay, there is a k, and means there is a clustering. Okay, so k is actually an hyperparameter here. So k means given a data, this is an unsupervised. Okay, so I'm not going to give the labels, unlike whether it's a diabetic or not diabetic or the salary. I'm not going to give anything for this particular data. I'm actually going to pass the bare data without the labels, and I'm allowing the machine to learn the parameters, the attributes of the data, and then come up with its own algorithm or the analysis. So, and in analysis, as we've already seen, you can actually get clusters. That is, you can have bell peppers, brinjals, and turnips. So you will not be able to know what is what, but you can actually differentiate that cluster A doesn't resemble cluster B nor cluster C. Okay, so that is the same idea that I'm going to, bring it to the script as well. So the working flow of a k-means is such that you start your analysis and you find out that elbow point. So what does an elbow point mean? So how does our elbow look like? So elbow is, you can actually put it into an XY 90-degree curve. Okay, this is your elbow, right? You have an arm here and you have your wrist over here. Okay, so this is your elbow. So what does an elbow mean? So elbow means it is actually, let me just remove it. Okay. So my elbow curve is going to be looking something like this. So elbow curve means I would like to find out that value of k which gives me a loss curve which looks like an elbow. That is a least loss curve. Okay. So how many clusters are needed for the particular data set to give this smooth elbow curve is nothing but the elbow point. That is a k. So I need to first find it out. Then I need to find the distance between the data points to make the cluster. So the one of the peculiar, the metric that is used to divide the data points into the clusters are nothing but the Euclidean distance. Okay, so there are 3 clusters, for example, and I have data points over here, I have data points over here, and there are data points over here. So depending upon the distance between these 2 clusters, okay, if it is too big, that means I can say these 2 points belong to 2 different clusters. But if I take a distance between these 2 points, I can say it is less, so they are more probable to be in a single cluster. So it is the idea of measuring the distance d. Okay, and then grouping them based on the minimum distance, and then repositioning the centroid. So again, you'll have a centroid for each particular classification clusters, and depending upon the centroid, you'll be calculating the distance. Okay, and if the clusters are again unstable, you will measure the distance and continue this process. If the clusters are stable, you will converge it, or you will stop your training process. Okay, so this is an idea of clustering. So now let us get into the script and see what clustering looks like. Okay, so again, let me clear the console. Okay, remove the variables. Okay, once more clear it. Okay, so now we are ready to train it. So for key means, again, I've taken a data set which is for housing. So it's a data set which shows the prices of house in California. Okay, so that is we are going to make an analysis, say what is the range of pricing in California. Okay, we are not going for a regression analysis here, mind it. We just want to know what is the number of clusters, or what chunks of housing prices are available in this particular data set. Okay, so now let me load this data set. Okay, so I've loaded the data set now here. So if I can open it up for you, see, I have a latitude, I have a longitude, so which will give me the idea about the location of this place, and then the associated housing value or housing price with this particular latitude and longitude. Okay, now let me use this Seaborn library. This is actually a very beautiful library which gives you a plenty of plots. You can actually explore the data visually and see how the data looks, how there are numerous plots. Okay, you can go back and explore it. So now I'm using a scatter plot with the home data, with nothing but my data frame, and my x-axis is going to have the longitude and y-axis is going to have the latitude, and the color of this plot is depending upon the median housing value. Okay, so depending upon the color of this housing, I'm going to get a plot. Okay, so let me just run this for you. Okay, so as I said, depending upon the color of depending upon the value of this median housing term or the variable, I have 5 clusters, and these area of California has been differentiated into these 5 clustering values. Okay, so if you see, if the value of housing is 5 lakh, the darkest point resemble them, and the light colored one resemble the least valued median housing. Okay, now again, I'm going to split the training and the data into training and testing. Okay, so that is how I've split it. Now I'm going to, rather than using standard scalar, now I'm going to normalize it. This is another approach. Okay, you can use any of this, which is going to give you the same, the use. So it's actually going to normalize a data point, whether it is depending upon your max minimum scalar or depending upon your standard scalar. It it can be chosen according to the data set or a use cases. Okay, so I'm using the normalize function right now, and I'm going to normalize it. Now I'm going to import these k-means object from the Scikit-Learn library, and I'm going to create an the object of this particular class over here. Okay, just a minute. So before you get into the coding, it's always good to get an hands-on on these documentation of these libraries, because often new updates come and older versions get deprecated, so it might affect your coding. So if such error comes, you can actually go back into the the errors and check the documentation whether the terms or the namings has been changed. Okay, so now I'm going to run it again. Now it's working fine. So now, as you have seen in the flow chart, we have actually told to start the analysis, find the elbow point, and then continue with the training. Okay, that is how the flow has been defined. But I am just going to train it blindly with 3 clusters and see what is the performance. Okay, so now I want my data to be clustered in 3 classes. Okay, the random state is 0 and the number of initializers are auto in this case. And now I'm going to fit my training data. Okay, so the data has been fit. Okay, now let me see the scatter plot again. Okay, now in the previous scatter plot, I had 5 classes. So I had 5 different values. Here I am having only 3 classes, that is 0, 1, and 2. Okay, 0, 1, and 2. Fine. So if you can see, the top portion of California has got a mediocre value, whereas my southmost portion of the California has got the least value, and the center California has got the highest housing pricing. Okay. So depending on this analysis is actually useful for people who want to, find a particular place or the area wherein they want to stay. Suppose your budget is too low, then you can choose somewhere in south. Or if you want a lavish house, or if you are okay to spend a lot, you can actually choose in a central one. Or if you want a mediocre choice, you can go for the northern California. So that is how these kind of analysis help you in real time. Okay, now let me go into a box plot. Okay, the box plot is going to show the density of values. If you can see, density of 0 and the second class is almost the same. So that means the northern and southern California has got, more or less houses of, that similar density, whereas central has got the least density, comparatively least. Okay. Now, one of the parameters that analyzes the performance of, k-means or unsupervised clustering is a Silhouette score. Okay, Silhouette score is nothing but it's actually measures the distance between the neighboring points or the neighboring data points. So the model with the least Silhouette score is going to be the robust one. Okay, so let me import this particular library, and I'm going to pass the explaining and the k-means label. Okay, and the metric for calculation is Euclidean distance again. Okay, so let me calculate the Silhouette score. It might take a while, a couple of seconds. Okay, so now my Silhouette score is 74.9% with cluster is equal to 3. Okay, but I do not know what is my, the perfect or the optimal value of k here, because I have randomly given it. Now let us go into the proper analogy of k-means cluster. That is, I have actually defined a range of k, taking from value 2 to 8, because beyond 8, there is no point in, dividing it in clusters. It will become a, a separate variable. So I don't want that to happen. So, and I'm defining 2 empty lists, which is actually the fits and the scores for each of these k value. Okay, now I'm going to run this particular for loop, which is going to train the model, that is k-means, on values from 2 to 8, and append the Silhouette score and give it to me. Okay, now let us see what it does. So I have given a print which says, running for k is equal to 2, running for k is equal to 3. So let us wait until the training process reaches k is equal to 8. It will take some while. Okay, so it's almost done. Yeah, so it has been running from 2 to 7. Okay, yeah. So at last, it has appended the scores and fits into these particular lists. Okay, now let me do a line plot with x-axis to be k value and y-axis to be the score. Score is nothing but the Silhouette score. So as I said, we need the elbow curve at the least value of k. So if you can see here, the value of Silhouette score reduces and reached the minimum at k is equal to 5. So for this particular data set, we can, go for k is equal to 5 without any justification, because the analysis says so that, okay, at k is equal to 5, you're going to get best performance. Okay, so let us see now whether the analysis is to the point or not. Okay, now I'm going to use a scatter plot also with k is equal to 5, and see how the values are distributed. So this is how the values are distributed for 5 clusters. Okay, now let me see a box plot analysis. Okay, so As you can see, the California region has been divided into 5 clusters, and these are the density of housing values for these 5 clusters. Now let me see what is the Silhouette score for k is equal to 5. Okay. So my training is done for k is equal to 5, and I'm going to find the Silhouette score. So we had received Silhouette score of 74.9 for k is equal to 3, and now it is 64.4, which is very less than the previous one. As I said, Silhouette score, the least Silhouette score is going to give you the best model. So definitely this is the at k is equal to 5, you're going to get the least value. So you, with this data set, with this model, you cannot go beyond this value, below this value for any value of k. Okay, that is the idea, because if you can again tweak the k means clustering with different random state and number of initializers, then the story gets different. Then you have to run the k and k value analysis, and then find out the minimum value of k, which gives you the optimal value of Silhouette score. Okay, so again we have done with this k means as well. Okay, coming back to our presentation. So we have done with this analysis as well. So the references to the data sets are also provided here. So this is actually the decision tree. The Pima diabetes dataset is taken from Kaggle, and for the regression, I've taken the dataset from GitHub. For clustering, again, I've taken the dataset from Kaggle. Okay, you can go into these links and reproduce these data codes and tune it further. Okay, so that was all I wanted to share it in this particular session. So thank you so much. Happy learning. Bye.